So chapter 4.3 is about inequalities, and they start you off with just linear inequalities. For instance, they'll say, let's give the line x minus 3, which of course goes through 0, comma, minus 3. And they say, well, we want to know everything point above 2. So it's clear when you do graphically that every point above 2 on the graph line starts when x is 5 and higher. So you can clearly see that happens in this case only in the range when x is bigger or equal to 5. So you can even put it in the domain of the line. But they want you to learn this chapter how to solve it algebraically. And it's very important to keep a couple rules in mind. One, absolute values require an extra rule. We'll get to that. Two, let's say I've got this as an inequality. When is minus 4x smaller than 8? When you divide by a minus to solve this, you must switch the signs. So this smaller than must switch to minus. So essentially that's the big and only rule. When you divide by minus on both sides, you have to switch the sign. So I get x is bigger than minus 2. The second big rule is always go back and test, because some inequalities, even though you solve them algebraically, still don't work. So I'm going to put minus 2 in here, and I discover when x is minus 2, it's 8 is smaller than 8, which is not true, but since this must be bigger than minus 2, I suspect that minus 1 will work. When I put minus 1 in there, I get 4 is smaller than 8, which is true. And when I put minus 3 in there, I get 12 is smaller than 8, which is not true. So therefore, this works, and I can discover it even more finally if I take minus 1.99 and minus 2.01. This one won't work, and this one will. So that's one of the rules. When you divide by a negative number, you must change the sign. Otherwise, they can be solved algebraically, just as if it said minus 4x is equal to 8. Therefore, x is equal to minus 2. Except in this case, we're having smaller and bigger signs. Now, inequalities are going to be used. Let's say you have this graphic line here. And it's not a big deal for linear lines. But when you get to something like this graph, and you want to know everything that's bigger than 2, if you don't have the graph, it doesn't work. But what you can do is you take this equation, and you're saying, well, I want to know whenever that is smaller than 2, right? In this case, it is, bigger than 2. In this case, it highlights the x values for you. But let's say you were just going to solve it algebraically. You would subtract the 2 on both sides. Okay. These cancel out, and these become 0. And then you would just solve it like you would any algebraic solution. Okay, let's see if it holds true. Do that. We're just going to take x cubed minus 4x and solve it. X cubed minus 4x, when is it bigger than 2? Well, we're going to take an x out of each of them. Oh, bigger than 0, sorry. We're going to take an x out of each of them. We get x squared minus 4 in the middle. That's a difference of 2 squares. So you get x plus 2 and x minus 2. And we discover several things. So when x is equal to 0, this will be 0. So therefore, one of the solutions is x must be bigger than 0. When we look at this one, when x is minus 2, it's equal to 0. Therefore, x must be bigger than minus 2. And let's see if this is going to hold true. And then finally, x is bigger than 2. Now, all of a sudden, you'll notice, all I've done is find the 3 areas where it's going to cross the graph. So let me just show you what the graph would look like above if I subtract 2 from it. is equal to. It's the blue graph, but lowered by 2. And by solving the inequalities, all I did was identify the x-intercepts. I discovered -2, this, and 2. But I did not solve where it falls above and where it falls below. And that will come from your knowledge of graphs. So you're going to say, okay, well, that's a cubic, and it's got a positive leading coefficient. I know it's going to start in quadrant 3. When I solve for 0, I discovered it goes through -2, 0, and +2. Since I know my cubics must go up and down and up again, I can see that this area here is below the graph, as is this area here. Therefore, the areas I'm interested in are here and anything above 2. So you can see you needed a knowledge of your cubics to solve that. However, you could have also placed a value that's below -2 into the equation. So let's say -3. You get -27 plus 12. And you can see that -15 is not above 0. So you know that, okay, -2 to the left of -2, just like your tables before, doesn't fit the rule. Then if you pick a number between -2 and 0, let's say -1, and you plug it into the equation, you get -1 plus 4, which becomes 3. And 3 is bigger than 0, so that you know, okay, everything between 2 and this is going to be above. Then when you plug in 1 into the equation, you get 1 minus 4 minus 3 is not above 0. You automatically know between those 2 points it doesn't fit the rule. And therefore, either algebraically or your knowledge of the graph, you can discover, okay, I'm above the line between -2 is smaller. If it's above, it's smaller than x and smaller than 0. And then I'm also above the line when x is bigger than 2. That's when it's above 0. So solving inequalities is going to tell you how to solve these graphs when, let's say, y is bigger than 0. But you had to lower it down by 2 to suddenly be able to solve it algebraically. You can't solve it without a graphic calculator, just by making it equal to 2. You have to bring that 2 to the other side of the equation, make it equal to 0, and then solve it like you have learned how to do. Otherwise, you'd need a graphic calculator. Now, notice that whether I make it bigger than 0 for this graph or bigger than 2 for this graph, I get the same information. And that's because when I subtract 2 from this graph, all I'm doing is lowering the whole thing by 2 and bringing it down to the x-intercept, which explains why this one, when solving for the x-intercept, gives me my answers. So whenever you want to know when a graph, in this case, we want to know when this graph is above 2, we can bring it down to the x-axis, solve, find the x-intercepts, and then rationally figure out which parts of the graph are above. Now, surprisingly, this has more scientific merit than most things you've done, because when you're studying biology, let's say, you're only interested in a certain group or population and when that population changed, and you're trying to isolate the factors that affected its population. Once you identify when it has changed, you can identify, okay, for instance, a bear population, let's say they're endangered, and you're trying to bring it up to a certain point. Well, you need to be able to measure if your environmental protections have impacted on the population. So looking at data and determining, being able to analyze data correctly is a big part of biology, it's a big part of chemistry, it's a big part of epidemiology. It's even part of medicines when your heart rate has gone up, gone down on average. And this kind of analysis is useful. So let's just get to the chapter. This chapter, again, looks at linear inequalities, and we're going to do a few of them. But you essentially just solve them for x, as if it equal it. And then you just keep the sign there And again, you always want to go back and test, and you always want to go to the end of the chapter and just see the basic rules. When you divide by a negative number, you must reverse the inequality sign. Most linear equations have one solution, whereas linear inequalities have many solutions, and the number line can help you visualize. The first three examples, and actually this entire chapter, is very basic. Okay, so we're going to just plow through a lot of them. Okay, using set notation. So I don't know if we've gone through set notation. This is linear notation. Let's say -3 is smaller than x is smaller than 3. And this is set notation. Now notice it's smaller and smaller. Set notation would use a rounded bracket when it's smaller. And you'd say -3, comma 3, rounded bracket, because it's just not smaller and equal, it's just smaller. That's set notation, saying here's the limits. When it's infinity, infinity always gets a rounded bracket. And let's say we're saying negative infinity smaller than, even if it's smaller than equal to x, which you'd never say, you just say smaller than x, smaller or equal to 3, when you have the equal sign and you put the 3, you're using a rounded bracket, like a squiggly. It looks like that. And that's when you have the equal sign in it. So that's set notation. So let's just get on with this. So we're essentially going to solve for 3x. We're going to add 1 to each side. We're going to divide by 3, positive 3 on both sides. And we discover when x is smaller or equal to 4, so that means if I had a number line and I have 4 here, I would draw it in solid because it's smaller or equals, and I would draw the line this way with an arrow. And when we go back and test it, sure enough, when this is 3, we get 8, which is smaller or equal to 11. When it's 4, we get 11 exactly, which is smaller or equal to 11. And when it's 5, we get 14, which is not smaller or equal to 11. So therefore, when we test it, the rule is true. Oh, and in set notation, since we say x is smaller or equal to 11, it's a good question. I don't know how to do a single variable in set notation, so let's just look very quickly at 1a. And that's not set notation, though. Okay, I guess this is set notation. No, it's not, though. That's just normal notation. This is set notation down here. So I guess because there's no, I guess because infinity. Okay, if I was going to do it in set notation, it would be rounded negative infinity, comma 4, curly bracket because it's smaller or equals. So that's how I would do it. I'd say it can go all the way down to negative infinity and 4. So yeah, I did know how to do it. It just wasn't a thing. But that's not set notation what they have in the book. They have in the book normal date notation, which says x is part of all real numbers / x must be smaller or equal to 4, close. That's how they have it in the book, which is, in my opinion, I don't believe set notation. Okay, let's go on, and I'll just do the notation in every way. We're solving b. Now when you add, so now we've got 9x, so we've got to subtract 5 from both sides. Now, we're going to divide by -1, which means I must change the symbol. So I'm going to get x smaller than +7. Then we go back and we test it. Let's take 7. If it's -7, because the 7 just goes in where the x is and the minus is then applied to it, +5, I get -2. And -2 is not bigger than 7, so we can see that 7 doesn't work. If I take 6, I get -6 + 5, I get -1, and -1 is bigger than -2. And if I take 8, -8 + 5 is -3, and -3 is not bigger than -2, so we can see that the rule fits. Which means if I'm going to do a number line, I would just do it here. I would this time put a hollow circle at my 7, and then the arrow is pointing to the left because it's smaller. If I'm going to do normal notation, since x is a part of all real numbers, but x is smaller than 7, very much how we've written it. And if I'm going to do set notation, I'm going to do a rounded bracket, because infinity is never curly bracket, comma, and what did we determine? That it's 7, and rounded bracket because it's smaller than 7. So we can see that when we test it out, we get the results we want, and that's what you always want to do. Test on either side of the number. Here, it doesn't matter how many, doesn't matter how many symbols there are. You can still add 2 to both sides, get 3x plus 10. Then you can, I probably should have brought that x to this side actually. Let's do that. Let's bring the 8 to this side and the x to that side. So I'm going to subtract 8 on both sides. I get minus 10, and it disappears here. And I'm going to subtract x on both sides, and I get 2x on the right side. That way when I divide by 2, I'm not switching the signs. Notice though that the x goes to the other side, and this is a good example of why you have to switch the signs. Instead of dividing by negative, I brought the x to the right side, which brought the little nose now pointing to the x before the big mouth was pointing to the x. And you can see now why you have to switch the signs when you divide by a negative number. Anyway, I get minus 5 is bigger than x, which means that x must be smaller than minus 5. Then you go back and you test it out. Let's take minus 6. So minus 6 minus 2 is minus 8. Is bigger than 3 times minus 6 is minus 18 plus, let's try that again. Must be smaller than minus 5, so I'm taking minus 6. So minus 6 is minus 8, must be bigger than minus 6 times 3 is minus 18 plus 8 is minus 10. Yep, minus 8 is bigger than minus 10. Let's try on the other side. Let's take minus 4. Minus 4 minus 2 is minus 6. Bigger than 3 times minus 4 is minus 12, plus 8 is minus 4. Minus 6 is not bigger than minus 4. And if I put minus 5 in there, I get minus 7 is bigger than minus 15 plus 8, minus 7. So you can see why it's smaller and not smaller than equal. So this is true. And writing it as set notation, I would go circle minus infinity, comma, minus 5, rounded brackets because they're smaller, not equal. And if I'm going to do normal notation, I'm going to do a bracket like that. Let's say x is part of all real numbers, big slash, x is smaller than minus 5, which is what we've written here. So I'm not going to write this anymore because I write it here. Just remember it always includes that information. By the way, if we'd done this one and instead brought the 3x to this side, I get minus 2x. And the 2 to the other side, I get is smaller, is bigger than 10. And then divided by minus 2 and switch the sign, we get the same information, the same result, which shows you that switching the sign when you divide by a negative number is necessary. Okay, going to this, you have a choice. You have to expand it because there's a 2x over here. If you divide by 3 first, you end up with a messy 2/3 x, which is still solvable, but it makes it a pain. So distribute it first. You get 6x plus 4 is bigger or equal to 2x. Bring the 2x to this side, you get 4x. Bring the 4 to that side, you get bigger or equal to minus 4. And when you divide both sides by 4, you get bigger or equal to minus 1. If you go back and put it in the original equation, and you can start with minus 1, you get minus 2 plus 4 is 2, times this is 6. Over here, is it bigger or equal to minus 2? It is. Let's try that again, because I don't think I did it probably. Minus 2 plus 4 is 2 times 3 is 6. Is bigger or equal. Now, that should have come out differently. So maybe I know what I did wrong here. this is 12, not 4. So I didn't do the distribution properly. You're probably screaming at the screen. That's what I did wrong. And if you bring 2x to the left side and 12 to the other side, that's what you get. And I spotted it because when I was plugging in -1 here, I should have come up with the same numbers on both sides. Okay, so now x is bigger or equal to -3. Let's try it out with -3. I get -6 plus 4, which is -2, times 3 is -6. Is bigger or equal to -6. So that makes sense. -6 is equal to -6. Since it's bigger or equal, if I take -4, it should also work. So if I plug in -4 here, I get -8 plus 4 is -4 times 3 is -12. And on the right side, I get, then this is smaller than -4, so it should not be true. I get smaller or equal to -8. We can see that is not true. So that makes sense because I chose -4, which is smaller than x. If you go ahead and do -2, you'll see that it's true. So in regular notation, it's XER and this. And in set notation, it is curly bracket because the equal sign, -3, comma, positive infinity, rounded bracket because infinity is never included as an equal. There's no such thing as a number infinity, so you can't equal it, I think is the logic there. Okay, moving on to E, same thing, distributed first. So I'm going to start just steamrolling through these instead of, I'm not going to test them out anymore, so I'm going to let you test them out unless it's incredibly difficult. So I'm going to bring the 5x to this side just to keep the x's on the left side. I'm going to bring the -2 to that side. And I'm going to divide by -1, which means I have to switch the sign. It means x must be bigger than 10 in set notation. Bigger than -10, sorry. In set notation, it is -10, rounded bracket, comma, positive infinity, rounded bracket. And you know how to do the other notation. Very quickly, if I put in -10, I get 1 minus 20, or 1 plus 20, 21, times -2, I get -42. And over here, I get -50 plus 8, which is -42. So you can see that -10 is right on the border. And I'm not going to bother testing the other ones because I know it's probably correct. Okay, and here's the last one. Well, how do you solve these ones? Well, the secret to get rid of any fraction on the side is you consider it all in brackets. And you multiply both sides by 5. It obviously cancels out here, and you're just left with the 6x plus 8. And on the other side, the 5 is multiplying everything in this bracket. That's why brackets are really important. And so you get minus or equal to 10x minus 20. And now I can rebalance everything. And I'll put all the x's on this side, on the left side. So I get minus 4x. Bring the minus 8 over here, smaller or equal to minus 28. And when I divide by minus 4, I get x is bigger or equal, because I divided by minus 4, to 7. Now when you go back in here, it should all work out. So I'm going to assume that's right. So in set notation, I get curly brackets, 7, comma, positive infinity, round bracket. And there, that's how you do number 1. Oh, interval notation. That's what I'm thinking of. Interval notation, yeah. So this here is interval notation. And set notation would be this, XER. slash x is bigger or equal to 7. Rounded these curly brackets. Curly. Okay, now we're going to go to set notation, or interval notation. Okay, it's the same thing. They just want you to practice your notation. So I'm going to steam through it. I bring the 4x to the left side, smaller or equal, I bring the minus 5 to the right side. I divide by -2, so I must change the signs. And there's my answer. And in interval notation, it's like this. Oh, curly bracket because of this equal, comma, positive infinity is the right side of it, rounded bracket. There you go. Check your answers in the back of the book. Same thing with this one. You have to distribute the left side. You get 2x plus 6, smaller than, and this -1 multiplies everything in the bracket. Smaller than minus x plus 4. Bring the x to this side, I get 3x. Bring the plus 6 to the other side, I get -2. Therefore, x must be smaller than -2/3. And when you test it out, you'll discover, sure enough, it should work out. Now, because this is a weird little fraction, I am going to test it out. So when x is -2/3 here, and I multiply by 2, I get -4/3 plus 3, smaller than, plus 2/3 -4. And sure enough, when I do this, I get -2 1/3 here. Or no, I get 2/3 here. 2 and 1. So this is -1 1/3 plus 2. So I get 2 2/3. Actually, I think I get 1 1/3. 1. Let's go back and do that again. Let's use the expanded version. So I get 2x plus 6 is smaller than -x plus 4, which is the same as 4 minus x. 2 times this is -4/3. That's what I forgot to do, plus 6. So that ends up, what's 1 1/3? If you want to just put it all in the same, that's 18/3. -4 plus 18 is 14/3. And on the right side, 4, what did I say it was? -2/3. So -2/3 is 4 2/3, if I got it right. Which means that this is 12/3, and 12 plus 2 is 14/3. So yeah, I got the same number. So -2/3 is indeed the correct answer. Sorry for bobbling around there. This one, you just simply multiply both sides by 3. On the left side, you get rid of the fraction. On the right side, when both those terms are multiplied by 3, I get this. Your algebra should be on point now. When I bring the 3x to this side, I get -x, smaller or equal. When I bring the plus 3 over to this side, I get -18. And then when I divide by -1, the sign switch, and I discover that x must be bigger or equal to 18. In notation, that would be curly brackets because of the equal, 18, comma, positive infinity, rounded brackets. To be honest, this should be child's play to you at this point. It's really solving it and just keeping the identities the same. When I bring the 5x over here, I get -3x, smaller or equal to -3. When I divide by -3, I switch the signs and discover that x must be bigger or equal to 1. When I put 1 in here, I get 3, and 1 in here, I get 3, so it's true. Yeah, I should take on either side to make sure, and you should in the beginning. And in a test, you definitely should always verify your answers. When I solve here and bring the x over to this side, I get minus 2x bigger than, bring the one over here, 0. When I divide by minus 2, I still must switch the sign, and it says x must be smaller than 0. When I put 0 in here, I get 1 bigger than 1, which sort of makes sense. When I put minus 1 in here, I get 2 must be bigger than 0, which is true. So that's true. And in interval notation, I do a rounded bracket, negative infinity is the left side, comma, 0 rounded bracket. And finally, the last one, how do I get rid of those fractions? Well, both 2 and 4 are factors of 4, so I'm going to multiply both sides by 4. When this happens on the left side, those cancel to 2, and the 2 must multiply both those terms, 2x plus 8. When I multiply the right side, the 4 just disappears. Now I bring the x over here, I get x is bigger or equal. When I bring the 8 over here, I get minus 10. In interval or interval notation, it's a curly bracket because of the equals, minus 10, comma, positive infinity, rounded brackets. And there you go. That's all of them. Solve the double identity. And okay, so double identities, so long as you keep all, when you, let's say, subtract 6, you must subtract all identities. So essentially you're treating 3 identities. And we're trying to figure out what x is smaller than and bigger than in numbers. Now it's easy like this. So the first step, we need to subtract 5, but that means I have to subtract 5 here and subtract 5 here. I get minus 2 is smaller or equal to 2x smaller than 12. I divide all sides by 2, and I get minus 1 is smaller or equal to x smaller than 12. And there you go. You now have a solution. And if you're going to do it on a number line, you do it here. You solid in your minus 1 because it's equal, so solid dot because it's equal. You've put your 12 over here and you put a hollow dot because it's smaller than. And then you just make your line a little bit darker in between, like that. And that's your number line. Okay. So in this one, they just give you an x value to see if it's true or not. So instead of trying to solve them, just plug the 2 into it. Is 2 bigger than minus 1? Yes. So that's a yes. 2 over here, you get 10 minus 4, so you get 6. And over here you get 6 plus 2, 8. Is 6 bigger than 8? No. 2 here. 3 times x, 6 minus 5 is 1. So you get 4 on here. Is 4 bigger or equal to 6 times 2, 12? No. 2 in here, you get 10 plus 3, 13. Is that smaller or equal minus 6 plus 1 minus 5? No. So a lot of them are no so far. 2 over here, you get 0. 2 here, you get 6 plus 4, 10. So far, yes. 2 over here, 16. Is minus 2 smaller than equal to smaller or equal to 10, which is in turn smaller or equal to 16? Yes. So that's a no, and that one's a yes. And finally, is 33 smaller? What is this? Minus 20 plus 3. So you get minus 17. Smaller than 54. No. 33 is not smaller than minus 17, so no. And that's all you have to do for those. Yeah, you could expand and solve algebraically, but I personally, since they're giving you a number, find it perfectly fine to substitute You always want to find the fastest, easiest solution. And then they continue with the practice. Solve algebraically and verify your solutions graphically, which means they want you to figure out on Desmos. But this is just a line, right? And this line goes through -2, -1 on the x-intercept. So it's 0, -1. And then it goes up by 2 each time, 2 y's to 1 x. And they just essentially want to say, when is it smaller on this side? When is the y's? When are the y's smaller or equal to 13? So if you know this intercept point here, so you just solve it. So 2x is smaller or equal to 14. X is smaller or equal to 7. And then when you put it in, it makes sense. 13 smaller or equal to 7. 6 makes it smaller. 8 makes it bigger and proves it's not true. And then if you graphically do it, you will indeed see a line here at 7, 13 on this line. And you'll see everything below that makes sense when it's a line. Some of it's just logical. So this one's a line that also has the same y-intercept at 0, -1. And it has a slope of -2, so it's going down. When is it bigger than -1? Well, clearly, they've already given us the answer when x is 0. So whenever it's bigger, when x is bigger than 0. Oh, hang on. Smaller than 0, because it's all over here. So when x is smaller than 0, this line will be bigger than where the y-intercept is. So that's just logical. Now let's just solve it. -2x is bigger than 0 because I bring this over here. Divide by -2, I have to switch the signs, smaller than 0. And there we get the answer that we logically deduced. When x is smaller than 0, the line is above -1, which is essentially what they're asking. When is that line above -1? Now what's interesting about this one is they're asking us about a line that goes through 0, -8. And they're saying, when is this line, and by the way, it's slope of 2, so it's going up. And they're saying, when is this line above which values of x through this line? Well, this line goes through 0, 12, right there, and has a steeper slope. So you might say, well, it never goes through, except that at some point down here they will cross. And at that point, this line will be bigger than it. Well, I'll show this to you graphically. But let's solve it first. Because all lines that don't have the same slope must cross. And it's at that point that one line is above the other, whether it's this one or this one that you're looking for. In this case, it's going to happen way in the negative because this line started way above it on the y-intercept. So we bring the 4x over here, I get -2x. Bring the -8 over here, bigger than 20. Divide by -2, that means I have to switch the signs, and I get -10. When x is smaller than -10, this line is above that line. Yeah, we can go in and test it, but instead, I'm going to show it to you visually. I'm going to give you the line 2x -8 and 4x plus 10 plus 12, was it? See? Yeah. And you're going to see they cross exactly at the -10, -28. And at that point, the blue line is above the red line. So all the points below this, the blue line is above on the y-axis to the red line. After that point, the red line is clearly above the blue line for the same x values. It's always for the same x values. So when x is 0, it's clear that this one is at -8, and this one's at 12, well above it. And visually, that shows you that in this area, when y is smaller than -10, oh, sorry, when x is small, no. Can I do it with x? Yeah, there you go. It shows that in that area, the blue line is above the red line. You can also find the x value, -28, and do it this way from that point onwards, but it doesn't tell you the x values then. And I believe you can also make one smaller than the other, and it will highlight the areas where this is true. Let's see. Yeah, they're saying here, when is, oh, sorry, it's supposed to be bigger. So they're saying, yeah, when x is smaller, and they put a dotted line to say it's not included. The graph, they don't even graph it for you, so you should just keep the two graphs on there to visually see it. And they're saying, yep, from that point onwards, the purple line is above the black line for y values. And that's, you know, when you see it, that you're comparing two lines, it makes sense. And it's also important in a lot of things we do, like pollution, gas emissions for cars. That's, you're all measuring something to make sure it's below a certain standard. Quality of food. Food can't carcinogen. You got to measure the safe. Like for instance, food has an acceptable level of insects in the cereal. So you have to be able to measure when that's safe. And don't get freaked out by that. People are freaked out by man versus nature. We're mixed in quite well. You have 100,000 creatures on you right now. So bring the 2x over here. I get 3x is bigger or equal than 15 when I bring the -15 over here. When I divide by 3, I get x must be bigger or equal to 15. Which makes sense because we're describing a line that goes through -0, -15, and another line that just has a slope of 2 and goes through 0, 0. So when is this line going to be above or equal to that line? When x is 15. And when you put it in, it makes sense. I'm not going to graphically draw that one. And they're essentially all lines comparing to other lines, if you want to look at it this way, but we're solving it algebraically. When I distribute, I get -20 plus 12x is smaller than 6x plus 16. Bring the x's over, I get 6x. Bring the 20 over, I get smaller than 16 plus 20, 36. When I divide x by 6, I get smaller than 6. So therefore, when x is smaller than 6, this line, which has a slope of 12x and goes in through 0, -20, will be below this line, which has a plus 16, was it? 6x plus 16? Yeah. Which has an y-intercept of 0, 16, and a slope of 6. So all below, when x is smaller than 6, this line will be below that line. And again, I'm not going to graphically do that. I don't think you need me to do it at this point. Okay. How do you solve this one? It's much easier if you get rid of the numerator by multiplying both sides, put them in brackets by 3. It'll cancel out here, and I'm left with x minus 2 on the left side is smaller or equal than 3 times 2x, 6x, 3 times -3 minus 9. So we're really dealing with the lines x minus 2. When is it smaller than 6x minus 9? When is it below? Solving for x, I bring the 6x over here, I get minus 5x. And bringing the minus 2 over here, I get smaller equals to minus 7. And here we have a very weird one when x is smaller or equal to 7 over 5. Now we can put this into graphics. Let's do the x minus 2 and divide it by 3. And let's do the other one, which was 2x minus 3. And we can even say, when is this one smaller? Did we say smaller? Or equal to this one? And it's going to show us. And what was our answer? Oh, so we got something wrong here. When is it smaller, equal? When is it smaller, equal? Oh, I see what I did wrong. When I divided by the minus 5 here, I'm supposed to switch the signs. Good thing I checked graphically. So when x is bigger or equal to 7 over 5. And sure enough, when we zoom in on this point, essentially where do they cross, we discover 7 over 5, which is 1.4. Now you might also say, hey, that's where the lines always cross, and you'd be right. Whenever you want to find out when two lines cross, you simply make their equations equal to each other, and solving for x is that's the only x point they're ever going to share together. So solving for x will reveal where they cross. Any two equations, even two parabolas, except two parabolas can cross in 4 points. Okay, there we go. And we're moving on now. 5's done. Notice the practice ones are a lot easier than the other ones, and that's because they want you to get warmed up. Find the qualities determinant 0 as the number of solution set. For the following, determine. So just plug 0 in. Is 0 smaller than equal to 1? Yes. Is 0 smaller than 4 smaller than 12? Yes. Is 1 bigger than 12? No. Is 0 smaller than 1 smaller than minus 1? 1 is not smaller than minus 1, so no. Is, this will make everything here 0, smaller or equal to 7? Yes. Is 6 smaller than 2 times 3, which is 6? Is 6 smaller than 6? No. So you can see yes, yes, no, no, yes, no. And that's just plugging 0 in for x. Solve the following algebraically, so very much what we're doing. Now, these are triple. So long as you do everything to each number, you're okay. You're trying to get this x all alone in the middle. So we're subtracting 7 from everything first. I get minus 12 is smaller than 2x. Is smaller than minus 8, or is smaller than, what's 11 minus 7? 4. Now I'm going to divide everything by 2. 2, 2, 2. And I get minus 6 is smaller than x is smaller than 2. And there you go. You've simplified this, and it's very much more clear. You could put it on a number line if you wanted to. You can test it out to see if it's true. I'm not going to do that, but you should. And you do them all like that. Whatever you do to one set of numbers, you must do to all of them. And you're focusing on what needs to be done in the middle. I need to add 1 to all sides to get rid of that 1. I get 12 is smaller than 3x is smaller than 24. And when I divide everything by 3, I get 4 is smaller than x is smaller than 8. So it's much clearer like that. You can't really see that up here. Which means that any number that I choose between 4 and 8 that is not 4 and 8 will make this statement true. That's all that means. Okay, what's going on in the middle here? I have a 9 being added to x. Whenever you're solving something algebraically, you kind of do it in reverse BEDMAS. So I'm left with minus 10 is smaller or equal to minus x, that's big deal, is smaller or equal to 4. Now I have to divide everything by minus, which is going to flip all these signs. So I'm going to get 10 is bigger or equal to x, which is bigger or equal to minus 4. I can rewrite that so that the smallest number is first. I get minus 4 is smaller or equal to x. See the nose still pointing to the minus 4, which is smaller or equal to 10. Therefore, we can see that x falls anywhere between and including minus 4 and 10, and this will make this equation true. Plug in 0 and you'll see it's true. So is minus 1 smaller or equal to 9, smaller or equal to 13? Yes. Okay, those are done. Same thing here. You have to distribute the middle before you can start subtracting. Don't think you can subtract the 4 as a start, even though that seems like reverse bedmass. This still fits into bedmass. The brackets are there. So you have to divide everything by 2, negative 2 first, because this bracket is treated as a married unit. When I divide everything by minus 2, I have to switch the sign. So I get 0 is bigger or equal to x plus 4, which is bigger or equal, and what's 6 divided by minus 2? Minus 3. Then I have to subtract 4 from all numbers, and I get minus 4 is bigger or equal to x, which is bigger or equal to minus 7, and now I put it in correct order. Minus 7 is smaller or equal to x, which is smaller or equal to minus 4, which means for this to be true, my x has to be between minus 7 and minus 4, including minus 7 and minus 4. And you can test it out. This one's actually quite a bit simpler. Sometimes they're not true, so you should always test them out. So first I have to subtract 10 from both sides. I get 49 is smaller than x, 7x, which is smaller than, what's 73 minus 10, 63. And when I divide by 7, I get 7 is smaller than x, which is smaller than, here's probably one of those situations, because this divided by 7 is, oh geez, what's going on? 21, 5, is it 6, 7, 8 is 56, 9 times 7. So 8 times 7 is 28, 56, plus 7, 63. I don't know what happened to me there. 7 must be smaller than x, which must be smaller than 9, which means for this to be true, you have to have a number that's 7.001 and 8.999 for it to be true. And the last one, you have to expand the middle first because it's a bracket. Actually, no. Yeah, you could expand, and I shouldn't just tell you to divide by minus 12 because it's confusing. You can also just expand. I think it's adding an extra step. And let's see if we get the same solution, okay? One we're going to expand, and the other we're just going to divide by minus 12. So first thing I got to do is subtract 12 from both sides. So I get 6 is smaller or equal to minus 12x is smaller or equal to 36. Then I got to divide by minus 12, which means I got to change all the signs. And that's going to make this difficult. I get minus 6 over 12, which is minus a half. Must be bigger or equal to x, which must be bigger or equal to, and so this was 32. We're dividing it by 12. Was it 32? 36? No, it was 36, and it's being divided by minus 12, so it's minus 3. Rearranging, it's saying minus 3 must be smaller or equal to x, which must be smaller or equal to minus a half. Let's see if it would have been easier just to divide things by minus 12. It's roughly the same. So we get rid of minus 12 in the middle. 18 over minus 12 is the same as minus 3. When I divide them both by 6, I get minus 3 over 2. And now I have smaller equals to x minus 1 in the middle. 48 divided by minus 12. Oh, I got to change the symbols. So it's got to be bigger or equal to x. Is bigger or equal. And 48 divided by 12 is minus 4. Then I got to add 1 to all of them. Minus 3.5 plus 1 is minus a half. Is bigger or equal to x. Is bigger or equal minus 4 plus 1 is minus 3. And then I've got to put it in the correct order, and you can see I get the same thing. Roughly the same. I actually found it we got rid of one extra step. So, there you go. Will I continue here? Do I have time? Oh, 19 questions. I think I can do a couple more. Create a linear inequality with both constant and linear terms on each side for which the solution is x minus 4. So now they just want you to sort of, you might say, well, what a waste of my time, but it helps you realize the connection of these things. So we're going to take a linear inequality with both constant and linear terms on each side. So we're going to come up with two solutions. So one way you can do it is like this. You can say, okay, I'm just going to multiply both sides by 2. And I'm going to subtract 1 from both sides. And now that's true. If I put in 4 here, I get 7. So anything must be bigger than 4 to be an accurate solution. So that's true. And that's a linear connection and a constant. Now, to get a different one, we're going to add an x to both sides. So I get 2x to here, bigger than 4x, 4 plus x. And then I can even multiply them both by 2. But 4x is bigger than 8 plus 2x. So this will also be true. 2x. So when 4 is put in here, I get 16. And over here, I get 16. So it must be, x must be bigger than 4 to make this true. Because over here, if I put in 5, I get 20. And over here, I only get 18. So that's another way of getting 2 lines on either side. That's a very easy question, but it helps you imagine what you're doing. Create a linear inequality with both constant and linear terms on which the solution is this. And it's quite easy since you can just start with the solution. Let is multiply both by 2. So you get 2x is smaller or equal to 3. And if I want to make both lines on each side, I can add an x to both sides. And this will still be true. Essentially, whatever I do to both sides, it will keep it true. Now, if I divide it by minus 1, we have to change the signs. So if let's say, divide both sides by minus 3. So now I get minus x. It's bigger or equal than minus x over 3 minus 1. Believe it or not, even doing something complicated like that keeps this solution true. So you just start with your answer and you work backwards. The following shows this number line. So they essentially want you to be able to read number lines. So we can see it's that minus 6 is smaller and equal to x is smaller and equal to 4. And that's because there's solid dots painted in. Right to there's the set notation. Create a double identity for which this is a solution set. Okay, so I can just add 3 to all things. So minus 6. Let's add 9. So I get 3 here. Smaller and equal to x plus 9 is smaller or equal to 13. So this is still going to be true. So it doesn't matter so long as you do everything. It's the same sort of thing. So long as you do everything to each of these numbers, the solution will be true. Okay, and what's number 10? which one of these has a solution? So it always helps if you put it in right terms. X minus 3 smaller or equal to minus 1 x minus 3 smaller or equal. Okay, so let's just do it. Let's just solve the left one. I'm trying to get x all alone in the middle. If I subtract an x from all these things, x minus x leaves a minus 3. If I subtract an x from here, I get 3 minus 2x. If I subtract an x from here, I get smaller than minus 5. So 3 minus 2x. I got to get rid of the 3. So I subtract 3 from every number. I get minus 6 is smaller than minus 2x is smaller than minus 11. Fair enough so far? Oh, sorry, minus 8 over here. So now I have to divide by minus 2. So I get 3 is smaller than x is smaller than what's minus 8 divided by minus 2? 4. Now I also have to change all the signs. 3 is bigger than x is bigger than 4. Now right away I can see a problem. 3 is not bigger than 4. If I rewrite this, 4 smaller than x, which also must be smaller than 3. So you can say, oh, this doesn't make sense. I suppose if I put in, if x must be smaller than 3 but bigger than 4, there's no possible solution. And you can try it out. Let's try with 0. I get minus 3, smaller than 3, smaller than minus 5. Nope, 3 is not smaller than minus 5. So no matter what I put in for x, that will never be true. What about this one? This one looks the same, doesn't it? Except that the symbols are changed, which could have an impact. So I'm going to subtract x from everything again, and I get minus 3 is bigger than 3 minus 2x, which is bigger than minus 5. I'm going to subtract 3 from everything. I get minus 6 is bigger than minus 2x is bigger than minus 8. I'm going to divide by minus 2, and I get 3 is smaller than x is smaller than 4. This makes sense. You can have a 3.5 and it fits the rule. And the reason this one didn't is because it's impossible to have an x value that meets all these criteria, but it is possible for this one because the signs are in the other direction. But just flipping these signs up here makes it clear why it works. So there you go. There's that. Consider the following graph. So I'll just take a picture of these last three and see if I can get through them. Consider the following graph. The question is, write an inequality that is modeled by the graph. Okay, so let's say we want to see where the red line is above the blue line. What's the definition of the blue line? It's a horizontal line. Its equation is y is equal to 3. What's the blue line? It's clear it goes through 0, 1. And if I look at its slope, it goes from minus 2 up by 1 and across this, so its slope is a half. So I can see the formula of the second line is a half x plus 1. That's the formula of the second line. So the question that they're asking is, when is this line, if we want to see when it's above, so we can just say when is it above that line. So when is a half x plus 1 above 3? If we solve this, we get a half x bigger than 2. That's when bringing the 1 over to this side. Multiply both sides by 2. I get x bigger than 4. So that means when x is bigger than 4, the red line will be above the blue line. And sure enough, look at that. That's if you want to find out when the red line's bigger than the blue line. If you did smaller, you'd get x smaller than 4, and you discovered the red line is smaller than the blue line at 4. If you did when is the blue line bigger than the red line, you'd say when x is less than 4. If you did the blue line, when is the blue line smaller than the red line, when x is bigger than 4. So you can see that there's multiple solutions depending on which line we're seeing is bigger or smaller than the other. Confirm the solution. Yeah, we did it. We did all of these. Depends what you're looking for, right? That's all that's saying. But you can see that the key point is right here when x is 4. That's when they meet. Okay. This is the standard formula for converting Fahrenheit to Celsius. Generally speaking, room temperature is considered 20, but people are most comfortable in this range depending on what they are. Write a statement of a double linear equality. Well, essentially when 18 is smaller, and we're working with Celsius, okay, well, I guess we can say is smaller than this, and smaller than 22, and then they'd want us to solve it. But this is for Fahrenheit. So you'd have to rearrange it for Celsius. But since they asked for Fahrenheit, let's go ahead and do it. You have to multiply both sides by 9 over 5, all sides by 9 over 5. Okay. On this side you get, there's no real simplification. So you've got 18 times 9, and you get 162 over 5. Let's just leave it like that for now. 162 over 5. And that gets rid of this. And this side, when you multiply it by 9 over 5, you get 198 over 5. Okay? So that just means that when f minus 32 is between these two fractions, you're comfortable. Now we've got to add 32 to both sides, and you get 182 over 5 plus 32 here and plus 32 here. And you might say, well, how do I add 32 to those fractions? You can either convert this to the simplest fraction. So 5 goes into 160 80 times. So it's 80 and 2/5. I believe that's right. Plus 32, which means when it's 112 and 2/5, smaller than the Fahrenheit, is smaller than, and what about this one? It goes into 195. Jeez, my brain's stuck. 195 divided by 5. 39. 39 and 3/5 plus the 32. So I kind of got this wrong somewhere. I think I put the 18 on the wrong side here. Yeah. I'll just work with numbers. What's 18? What is 18 times 9 divided by 5 plus 32? 64.4. So it's saying, I totally got that wrong. So 64.4, whatever it said, is smaller than Fahrenheit, is smaller than, and now let's do the other one. What is 22 times 9 divided by 5 and add 32? 71.6. So that means that when the room temperature is between 64.4 Fahrenheit and 71.6, or whatever hell I came up with, that's when you're most comfortable. If you're writing it for Celsius, you don't even have to convert anything. You would write it like this: when 18 is smaller than the Celsius is smaller than 22, that's when you're most comfortable. In case you didn't know what I did there, I essentially replaced the middle term with the equation. and then I got to solve for f. So to get rid of this 5 over 9, I can either distribute it first, or I can multiply it. If I distribute it, I get 5/9 f, so I'm still going to have to multiply sometime, minus 160 over 9. So you can see it still doesn't work out. So what I preferred to do was multiply by its reciprocal to get rid of it, but I have to do that on all sides. And that's how I came up with the numbers I came up with. So you can either multiply these and turn them into decimals, you might as well, and then add 32 to both sides to get f all alone in the middle. And finally, 13, some volunteers are making long-distance phone calls to raise money for charity. The calls are billed at a rate of 50 cents for the first 3 minutes. So that's first 3 minutes are 50 cents and 10 cents a minute for each additional minute thereof. If each call costs more than $2, if each call cannot cost more than $2, how long can each volunteer talk on the prospective call? So first 3 minutes at 50 cents is $1.50. So you can just do that first 3 minutes like that, and then you can just say plus 0.1x or 1/10 x must be smaller than 2. So all I'm saying is I'm assuming you're going to be on the call at least 3 minutes for $1.50, and then every 10 cents after you can either express it as 0.1x or 1/10 x. So your first step is you have to get rid of that 150. So you subtract 150 on both sides. So 1/10 of x must be smaller than 50 cents. And we'll might as well 0.5, which is the same as 1 over 2, right? $0.50 is 1 over $2. I'm keeping everything in dollars, essentially. To get rid of this, I have to multiply by 10 on both sides, and I get 10 divided by 2. So x must be smaller than 5 minutes in order to keep this call under, or is it minute? Yeah, 5 minutes, which makes sense because 5 times 10 cents is 50 cents. When I'm adding 50 cents to $1.50, I hit $2. So I cannot go over 5 minutes here after the first 3 minutes, right? So you got to remember that we've already accounted for 3 minutes here. So there's 3 minutes here, and then we get 5 more minutes of x. So that means the total minutes must be smaller. X time must be smaller than 8. Now I think it would have also worked if I'd included x in the first one, and I said 0.5x plus 0.1x must be smaller than 2. Let's see. So 0.1x plus 0.5x is 0.6x. Must be smaller than 2. I have to divide by 0.6 on both sides. And if I take 2 and divide it by 0.6, I don't think it'll work. No, it doesn't work because x here is a different x compared to here. So it's easier if you just say, okay, the first 3 minutes is $1.50, and you just tag on a 3 there. So that represents 3. So if you do 3, if you do it like that, and you say, okay, first 3 minutes are $1.50 plus 0.1x must be smaller than 2. Now it'll work out to 8. So you get 0.1x, and so that's 3 minutes. Are we working in minutes here? No, that doesn't work. Might work with minus 3. So minus x is smaller than 5, and when I divide by 5, no, that still doesn't work. Oh well. the way I just did it does work. You just have to remember that the 3 minutes is definitely part of the first call, and that you can only afford 50 cents more, which accounts for 5 minutes, which is 8. So x must be smaller than 8, or minutes must be smaller than 8. Now, algebraically, I did not come up with the correct calculation. So it must be smaller than 200 cents. I think I can do it like this. I think it can be 0.5 plus 0.3, 0.1 divided by 2. So the average call times x, because that's the average. Except that that doesn't really work, because this is average for the 3 minutes and this is the average for the 5. So that doesn't work either. I think you could do 3 times 0.5, which is what I did, plus 5x, or 0.1x. That's what I did anyway. I assume the first 3 minutes. But you have to account for the 3 minutes in there. So 3 times 0.5 is $1.50, plus 0.1x. That means 0.1x must be smaller than 50 cents, which means x must be smaller than 5, except I've already had a 3-minute call in there. I've already had 3 minutes accounted for. I mean, this algebraically works, although you have to remember that you threw a 3 minutes in there. And if you look at your answers, I believe that's what you'll get. 18 minutes. Did I misread that question? Let's try that again. First 3 minutes. Oh, I think they're saying 50 cents total for the first 3 minutes, which is weird. And then it's 10 cents a middle. So, yeah, so they're actually saying 50 cents for the first 3 minutes, plus 0.1x, so that's a little bit weird how they phrased it. Must be smaller than $2, which means 0.1x must be smaller than $1.50, not 50 cents. And when I divide by 0.1, I get x must be smaller than 15, but I've already counted for 3 minutes, so 18. So poorly phrased question, because rate for me, that's a flat rate for 3 minutes. So I guess that's just my misread. And we'll do 14, 15, and 16, because I still have a bit of time. Find the equation that allows for the conversion of Celsius to Fahrenheit by solving the relation in question E. Okay, well, as I remember, Celsius is equal to 5/9 Fahrenheit plus 32, I think. Let's try that out for, so now they want you to solve for Fahrenheit, right? So that's one equation for Celsius. Let's just make sure that's the right equation. Oh, it's F minus 32, 5/9. Okay, F minus 32. So it's like this. 5/9. F minus 32, and they want you to solve for F now. They want you to have an equation where F is equal to something. So what it is 9/5 times Celsius, like that, plus 32 is equal to Fahrenheit. That's what happens when you isolate the F. The first thing you do is you multiply by 9/5 to get rid of it. then you add 32. And that's what you get. So this is the equation for Fahrenheit. This is the equation for Celsius. So if you know Fahrenheit, you can figure out Celsius. If you know Celsius, you can figure out Fahrenheit. Now they want to say, what values of C is the Fahrenheit temperature greater than the Celsius? So when is F bigger than C? Well, it's when this equation here is bigger than this equation here. So when is F bigger than? So I guess you can say when is this going to be bigger than the Celsius? Yeah, but this is a Celsius equation. So when is Celsius going to be bigger? So this is the Fahrenheit temperature. When is it going to be bigger than the Celsius temperature, essentially? Like that. So when is this Fahrenheit equation going to be bigger than the Celsius? So you can isolate everything. I'm going to multiply everything by 5. I get 45C plus 160. Oh, sorry, I get 9C, sorry. 9C plus 160 bigger than 5C. I'm going to bring the 5C over here. 4C is bigger than minus 160. So when C is bigger than minus 80 minus 40. Let's see if that's true. We're going to do two equations here. And we're going to do this equation. So according to me, sure enough, there it is. The red line is above the blue line when Celsius is minus 40. Now, I suppose I could have used these equations and made them equal and made this when is red line bigger than this, and that's another way to going about it. But instead I just said I'm going to make Celsius equal to one side and make the formula for Fahrenheit, which has Celsius equal, bigger than just the Celsius. There's no need to put a formula in for Celsius, seeing as I'm just saying when is it bigger than the C. And you can solve for C, or you can do it like this. You can have these two equations. And you can say, when is this red line bigger than this blue line, which are essentially just keeping the constants x instead, and you'll get the same solution that I just got. X has to be smaller than minus 40. Go ahead and do it with this one if you want. See if you get the same answer. Oh yeah, okay. The inequality. Yeah, so these absolute values are, you'll find them a pain. And let's see if I still, no I don't. So I'll just take a picture. And how you solve an absolute value, you have to remember from last year, functions 11. But you essentially solve it once for what they have. So you just solve it normally. When is 2x minus 1 smaller than 7? And then you do another one here where you multiply negative 1 times everything in this bracket, 2x minus 1, bigger than 7. Now let's see if that's true. So over here, when I do 2x minus smaller than 7, I get 2x smaller than 8 when x is smaller than 4. So x is smaller than 4 is 1. And over here, when I multiply it, I get minus 2x plus 1 bigger than 7. When is minus 2x bigger than 6? When x is bigger or smaller than minus 3. Now, right there I did something wrong. So I think I just keep the sign the same if I multiply by minus 1. So yeah, I think I just keep the sign the same. My bad. So you just take x is bigger than minus 3, which means that on a line solution, it will be between minus 3 and not including it, and positive 4. And to do this, you take your original equation and you put in minus 3 to see what you get. So you get minus 6, minus 1, minus 7, absolute value is 7, smaller than 7. Then you put a value in between the two, like 0. So you get absolute value of minus 1, which is 1, which is indeed smaller than 7. Then you put 4 in, see if you get 7 exactly, and sure enough, you get 7 exactly. So it's clear that it's between those. So when solving this right side, yes, you can multiply all these terms by minus 1, just don't change the sign. I also believe that you can do it like this. You keep the left side the same, you change the sign, and you put a minus in front of this number, which I think also works. So you get 2x is bigger than minus 6, x is bigger than minus 3. Yeah, that's the thing. You either change the symbol of the sign of the right side number with the sign, or you just multiply the entire left side equation by minus 1 and you keep the sign and the number the same. Which makes sense because there's got to be an opposite values, negative values of this formula that will make this true. So if you put this in a Desmos as well, you will see the solution. Was this it? Yeah, there you go. I think it does it anyway. Oh, let's see, was it? I think I got the equation wrong though. 2x minus 1. There you go. And it's from minus 3 to plus 4, and it highlights for you. You can always put this equation in there as well in the next one, and you can see, and then you can put when is y smaller than 7, and you can see the points on the green line that are below the purple line, and they also happen to cross with our values we got. But absolute values, inequalities, throw that little curveball because you've got to calculate the second one. Will the solution to the double equality always have an upper and lower limit? Only if it's possible. For instance, the absolute 2x plus 1 can never be smaller than negative number, any negative number. And that's because whatever I make absolute value in here, especially when I add 1, will become a positive number, which can't possibly be smaller than a negative number. So if there's a solution, you will always have a double equality. It'll either be outside the number line, that way, or inside the number line, that way. Okay, some inequalities are very difficult to solve algebraically. Here's an inequality. Explain why solving this equality might be very difficult algebraically. Because you have to learn how to do logs. To get an exponent, and any log of the left side, you have to do the log of the right side. So then you will also have to know your log rules for addition. And it can get very complicated. What's another way to do it? You could put it in a graphics calculator and see when this function is below the line. You can also use some table of values. So this is where you helps to know your equations. Okay, so you're talking about a line here, right there. A normal line, too, at that. It doesn't have a weird slope. And it clearly goes through the point 0, 1. And you can easily come up with several other spots. It goes through -1, 0. It goes through 1, 2. It goes through 2, 3. It goes through 3, 4. Then if you look at this one, it's a growth curve that's been lowered by 3. And you should know some basic numbers on your growth curve right away. Some basic numbers on your normal growth curve are when x is 0, you're going to get 1, and when x is 1, you're going to get your base. But all these have been lowered by 3. So you can do when x is 0, it's going to be -2. When x is 1, it's going to be -1. And then you can just throw in some values in here, because already we can see we're down here. If I graph it in blue, we're down here. And we're waiting until this growth curve is passing the x curve. So we can put in some values and see if we can find the actual crossing over. So let's put in 2. So 2 to the 2 is 4, -3 is 1. So there we got 2, 1. We're very close. 2, 3 is that. When we put in 3, we get 2 to the 3, which is 8, -1 is 5. So 3, 5, and this one is 3, 4. So somewhere at about 2.5, it crossed the line. So you can see that the numbers aren't perfect, so they don't match the line. So it's very hard to see where they would cross. But it's somewhere around 2.5. So that means the growth curve will be below the line, somewhere around x is smaller than 2.5. You can also try to solve it algebraically. 2x minus 2 to the power of x minus x must be smaller than 4. All right. If I take a log, I get 2x minus x, which doesn't help at all, smaller than the log of 4. I believe I can separate. I'd have to look at my rule of negatives. I believe it's the same as x log 2 divided by log x. So you can see it gets quite complicated, and I'm not even sure I can do it. So what I'm going to do instead is I'm going to put one function here is equal to 2 to the power of x minus 3. And I'm going to put the other function, g of x, is equal to x plus 1. And we're going to see where they cross. They do cross between 2 and 3. And then you can just say, when is f of x smaller than g of x? And notice that they cross twice because the line keeps going down and the growth curve flattens. And so you can see it's between roughly 2.5 and negative 3.935. Very hard to solve algebraically, but very easy to solve graphically. And I'm going to brush up on my logarithms for that, because there's a way to find out a very, not easy, but a log equation. Until you learn your logs quite well. You'd have to look up, for instance, log rules. And the key one is going to be, where's it good? There we go, right there. The key one is going to be, yeah, even then, it's not very clear. Be very hard to solve algebraically. Anyway, the table of values got pretty close. I just forgot to take, I forgot what the growth curves looks like that, and that the line will cross it twice. So I could have taken some table of values over here and estimated where it crosses on the left side, which is negative, close to negative 4. Not a great answer, but some operations result in switching the direction of the inequality. Cubing both sides. That's a good question. Squaring both sides. Oof. Making each side the exponent with 2 as the base. Well, those are all tough questions. I believe the 2 won't matter, because 2 times 2 times 2 is smaller than 2 times 2 times 2 times 2 times 2. It's essentially 2 to the 3 smaller than 2 to the 3 plus 2 to the 2, which is plus 4. And 2 to the 3 will always be smaller than 2 to the 5. Making each side the exponent with 0.5 as the base, so a shrink. So half to the exponent of 3 is smaller than half to the exponent of 3 plus half to the exponent of 2, so I think that's still fine. Replacing the reciprocal of both sides, taking the reciprocal of both sides. So 1 over 3 will be smaller than 1 over 5. No, that's not true. So you'd have to switch the sign for reciprocal. Rounding both sides up to the nearest integer. That's not true either. I don't think flipping the sides is the solution, though. Square root of both sides is fine. So that means square of both sides is fine. Cubing both sides is the question is for negatives, though. And actually, no, squaring will create a positive, so that won't always work. You have to throw a negative in front of the negative 1. Cubing will be fine, though, I think. Interesting. I'm curious what they say. And I really couldn't tell you. I'm not good at the theoretical stuff. So here they say it's maintained for A. It's maintained if they're positive but switched if negative, which is what I'm saying. Maintain, switch, switch, maintain, maintain. So I'm just going to grab that and compare it. And actually, I'll grab it with 19 as well. And we'll grab the textbook and 18 and 19. So they're saying cubing both sides, it's fine. Squaring both sides, you have to switch if one side is negative. Like I said, making the base of 2 is fine, and making the base a half is fine. Taking the reciprocal, switched, unless one is positive and the other is negative, which makes sense. Rounding both sides up to the nearest integer is maintained except when except when they become equal. Okay? Taking the square root of both sides is maintained, but undefined for negative numbers, which makes sense. And then they say solve for each. So they're essentially taking 19 and throwing some practical solutions in there. So I've pretty much got 18 without going into too much depth. How do we solve for this? We have to take the square root of both sides. So x is smaller than 2, or x is bigger than minus 2. How did I come up with that? Because if this was equal, and I took the square root of both sides, I come up with 2 answers. Since I'm going to take the square root of 1, I know that it's true for that. And if I'm going to take the minus 2, I'm going to switch the signs. And it makes sense. And sure enough, that's what they come up with. So it's actually easier when you just solve it for 0. So here we can see similar thing. You get 4x squared is bigger or equal to 36. You divide it by 4. When is it bigger or equal to 9? When x is bigger or equal to 3, or x is smaller or equal to minus 3. And sure enough, answers go. That's what they get. Smaller equal, bigger equal. The absolute value we've done. First you solve it. So essentially they're all the same. First you solve it for when it's normal, and then you switch the sign. So you solve it normally first. Bring the 2 over. When x is smaller than 3, then you just switch the sign and make the other number negative. When x is bigger than -5. So it's going to be between 3 and -5, which is what they have right here. And then the last one is the same thing. So you just have to be very good with your numbers. When I divide by -3, I have to switch the sign. And I get minus 21. And does that make sense? 27, sorry. And the cube root of -27 only has one solution. There's no positive answer. It's only going to be smaller or equal to -3. And that's what they have here. Oh, 3? Oh yes, 3 is in there because of the minus. So if I put 3 there, or -3, so I can see that it can be smaller than -3 or smaller, or it can be -3 or 3, and this -3 will make this big. No, only -3 works though, because a positive will make this negative, which is not bigger, but a negative number will make this positive, which will be bigger. So it can only be when x is smaller or equal to -3. I believe they have it wrong there. They have it smaller than 3. That does not work. 3 would produce a negative number, which can't be bigger than a positive number. So they actually got this one wrong.